So anyway, from a, so yeah, you're going to have a conservation point of view and, or a sort of evolutionary point of view. From the evolutionary point of view, these things are actually important. This turnover of the flora and fauna allows for this adaptive radiation stuff that we've talked about in Galapagos finches, Hawaiian Drosophila, mammals radiating after the extinction of the dinosaurs, stuff like that. So that's, the world refilling those kinds of ecological niches. So as a macroevolutionary pattern, there are several things that are kind of triggers of adaptive radiation. One is what we're really talking about now, is this ecological opportunity, right? So the Hawaiian Drosophilids can get to a set of oceanic islands and speciate really rapidly because of a lack of competitive pressure, because there's kind of new territory of these oceanic islands, right? Alternatively, you can have a whole set of competitive fauna that gets wiped out and then replaced by a new set of fauna like mammals and dinosaurs. You can also have morphological innovation that causes, that sort of opens new niches that can then be filled. So things like, the invention of flight in insects and birds and bats allows for a whole new set of kinds of organisms. So you don't think about them very much probably, but bats are one of the most diverse groups of mammals. There's lots and lots of species of bats because of this morphological innovation that opens this ecological opportunity. So I think this is the last major topic in this kind of set of stuff, is when you have these big scale patterns of evolutionary change, how fast do they occur? What are kind of the rates of change that you'd expect? And there's been this kind of historical dichotomy between stasis and gradualism. So you can imagine what gradualism means, right? Change occurs gradually, slowly, proportional to time, right? Idea that most evolutionary change is continuous, slow. That's the kind of process that Darwin imagined. Stasis is the idea that things are not changing very much most of the time. But obviously things do change over time, and extinctions and adaptive radiations are one of these things that causes sort of a burst of innovation, right? So an idea was proposed, is called punctuated equilibrium, which captures both those things, right? So the idea here is that most evolutionary change occurs rapidly but concentrated into relatively short periods of time. And the rest of that time, there's typically stasis or not much change. So again, Darwin had this gradual, slow plodding rate of evolution kind of viewpoint. This predicts lots and lots and lots of intermediate forms in the fossil record, right? Because each lineage of organisms spends lots of time traveling through these different kinds of intermediates. And of course, lots of intermediate fossils are found. You've looked at that, right? Darwin basically attributed the appearance of stasis in the fossil record to the incompleteness of the fossil record. Darwin basically argued that stasis is not real. That if you really had a complete fossil record, you would find all these slowly graded intermediate kinds of steps. And Eldridge and Gould, this is Niles Eldridge and Stephen Jay Gould, in the early 70s, they published this idea that, wait a minute, stasis is real. This is actually an evolutionary phenomenon that we should be thinking about and talking about and explaining. That stasis is not an artifact of an incomplete fossil record. It's part of the process of evolution that we should be studying. So stasis was these long periods of time where species change little morphologically. In other words, they're in some kind of equilibrium with their environment, so they're not changing, right? That's the equilibrium condition is not changing. And then sudden changes kind of punctuate that stasis so that you get rapid change associated with speciation events. And you can kind of even picture these as different kinds of phylogenetic trees. Now, before we get into this, when the phylogenetic trees that we've looked at before, this axis in this direction didn't mean anything at all, right? It was just our spreading the taxa onto the paper. In these kinds of trees, this axis does mean something. It's morphospace, morphological divergence, it's degree of divergence. So on these, it's not quite, I don't want you to be fooled into reading them exactly the same as other phylogenetic trees that we've talked about, but which of these represents the idea of punctuated equilibrium? Quick, it's a poll. Which one's the right side? That one? So which one seems to represent more, what did I ask you? Punctuated, right? Which one's more punctuated? The one with more commas and exclamation points? See, I'm just seeing if you're awake. So what's this tree saying? Ugh. You have these evolutionary lineages that are going up. Are they changing in morphology? What's a line like this doing? Marching along in time. Is it changing in morphology? So it's in some kind of static equilibrium, right? Then you get these branches that go out sideways. What are those? Changes in morphology over how much time? Not a lot. Rapid, right? So, and then the other thing from this kind of tree that you'll see is that if we go way in, you have, oops, go away. You have here a node, right? And here's some kind of descendant taxa over here, but the mother taxa continues, right? So you have speciation where you get branching off of one kind of thing from another, but that other ancestral type form doesn't go extinct or disappear necessarily. It might. So the one on the right is obviously representing a gradual kind of changes in morphology where you get these lineages, constant, slow change across these kind of lineages over time. And when they proposed this idea, it became this hugely controversial thing for a number of reasons. And in part because, they're saying Darwin was wrong about the gradual view of evolution. Also in part because they're paleontologists and the people responding and reacting were sort of population geneticist type evolutionary biologists. Paleontologists might say speciation's instantaneous. When they talk about rapid change, right, or speciation being instantaneous, that in geological time might be 10,000, 100,000 years of successive ecological changes, right? Something that a population geneticist would never say 100,000 generations is rapid or instantaneous, but a geologist, a paleontologist, might say 100,000 years in layers of rock strata is essentially instantaneous, right? To prove this, you need, or to test this, you need a group with a really well-known phylogeny that preserves lots and lots and lots of fossils, and one group that has been good for that is these things that are called bryozoans, which are like sponge-type things. And hopefully what you can see from this, help, there. These kinds of trees, so the dots are fossil data points, and the tree is inferred phylogeny around them. So if this is a tree of data from Metrorhabdotos fossils, what does that, yeah, you say it. Metrorhabdotos. What does this fossil data set support? Gradual change or stasis and punctuation? Stasis, right? You have this scale, if you didn't notice, is in millions of years. So you have, this thing from about 1.5 or 2 million years ago down to 7 or 8 million years ago that is no recognizable changes in that lineage over whatever that is, a 7 million year period. So at this point in time, biologists have sort of no trouble accepting the idea that stasis is real. There's lots of gradual change in lots of lineages of organisms, but there's also lots of punctuated equilibrium, especially for morphology. So we talked about this the other day when we talked about horseshoe crabs having very, very conserved morphological body form, but a great deal of evolution in their molecular machinery and immune system type stuff. Things don't stop evolving. Here's a tree that's alive now. They're called ginkgos. They're some planted on campus. They're used as ornamental trees on the other side of campus. And they have a very, very distinctive leaf shape, and there are 40-million-year-old fossils of ginkgos that have exactly the same kind of leaf shape. So these things are sometimes called living fossils just because they're still here and alive with no recognizable kind of morphological change over long periods of time, many tens of millions of years sometimes. So then this question is, if we now think that stasis is real and true, at least for some especially morphological features much of the time, then why is it true, right? And probably the most important answer to this is stabilizing selection, right? If you have a morphology that is good at doing something like extracting resources in a horseshoe crabby type of way, then there's selection to maintain that type of morphology. So if there's ecological stability for the kinds of resources and the way that you extract them, then there's selection pressure to not change, right? So stabilizing selection is going to be a very big part of the answer here. But again, the point is that this does not mean that the organisms are not evolving and adapting. They are, but not in gross morphology, which is what paleontologists have available to them in fossils. So, David, wake up. David, wake up. Just kidding. All right, that was the last slide. That's the first slide. Are there questions on that? No? All right. So,